Hi, respective teacher, and good day, everyone. Today, we will be discussing the uh, task of 4G radio network planning and optimization. As we will know, 4G technology have revolutionized the way we use our mobile devices by providing a faster data speeds and more reliable connectivity. So first, let me introduce my group member. Uh, we have three members, which are me, Lina, and Faisal. Um, and here, since new technology have emerged and the need for mobile data has increased, 4G networks have become an essential component of contemporary communication systems. The planning and optimization of a 4G network, which entails a number of processes to guarantee that the network provides a consumer with high quality communication services, are essential to the network's success. The second point is 4G LTE evolution. Since 2008, it released the version 8. It provided a peak download speed of up to 100 megabit per second and upload speed of up to 50 megabit per second. 2009, it released the version 9. Carrier aggregation allow many carriers to be used at once. Increasing speeds, version 9 supported wall LTE and improved multimedia broadcast, multicast, and service EMBMS. 2011, it released version 10. It added LTE Advanced carrier aggregation, which is permitted up to 5 carriers. Increased data transfer speed in LTE Advanced. 2012, it released version 11. This standard improved network efficiency and speed. Coordinated multi-point COMP transmission increased network efficiency. 2014, it released version 12. It enhanced network capacity and coverage. LTE unlicensed LTE-U increased network capacity by using unlicensed frequency. 2015, it released version 13. It concentrated on facilitating the Internet of Things. It introduced brand new capabilities including narrowband IoT, NB-IoT, which gave IoT devices a low power, low cost option. Here is the basics of radio networks planning. The scope of radio network planning includes several aspects such as coverage planning, capacity planning, site selection, RAN design, backhaul planning, frequency planning, and network optimization. Coverage planning involves identifying the areas where the network needs to provide mobile services and determining the necessary infrastructure to provide coverage in those areas. This involves considering factors such as a terrain, building structure, and signal strength. Capacity planning involves estimating the amount of traffic that the network will need to handle and designing the infrastructure to support the capacity. This includes determining the number of sites needed, the amount of spectrum required, and the type of equipment needed to support. And here is LTE system requirements. A long-term evolution is a 4G wireless communication protocol that offers mobile devices fast data transfer, base station, a core network, and user devices make up the network infrastructure needed for the LTE system. The LTE system offers a high-speed data transmission rate with minimal latency and better spectrum efficiency while operating in permitted frequency range. The LTE system makes use of MIO and OFDMA technologies to boost network efficiency and deliver a top-notch user experience. Here is LTE radio fundamental. So OFDMA is the key component of LTE radio technology that divide the frequency spectrum into smaller subcarriers. These subcarriers can be allowed to various users, which allow for the efficient use of the spectrum and helps to increase capacity. MIMO technology is another important component of LTE radio technology. MIMO employs multi-antennas to increase capacity and improve network performance by using multiple antennas. MIMO can provide spectral diversity, which allow for better signal quality and increased data rates. The LTE radio support a number of coding and modulation protocol needed to transfer data via wireless channel. These protocols have to ensure that data is transmitted accurately and efficiently. LTE support a variety to coding and modulation scheme, include QPSK, 16QAM and 64QAM. LTE FDA and LTE FDD and TDD. Frequency division duplex and time division duplex are the two different operating modes used by LTE. Time division duplex, whereas uplink and downlink transmission are time separated on the same frequency band. In TDD mode, uplink and downlink transmission are separated by using different frequency band. In FDD mode, the decision between FDD and TDD mode is influenced by a variety of elements, including user demand, network requirements, and spectrum availability. Here is FDD versus TDD modes. In FDD mode, uplink and downlink transmission are separated by using frequency band. This means that one frequency band is used for uplink transmission and separate frequency band is used for downlink transmission. This allows for simultaneous two-way communication, but it can be limited by the availability of frequency band. On the other hand, TDD mode separate uplink and downlink transmission by using the same frequency band. Uplink and downlink transmission are time separated, which is allowed for two-way communication on the same frequency band. This mode is more flexible than FDD because it doesn't require separate frequency bands, but it can be limited by the time available for each transmission direction. The decision between FDD and TDD mode is influenced by the variety of elements, include user demand, network requirement, and spectrum availability. FDD is used in applications that require a high quality voice service, while TDD is often used in applications that require high-speed data services. Additionally, the availability of spectrum can also influence the decision between FDD and TDD modes. Here is a LTE frame structure. The LTE frame structure is the time division multiplexing scheme divided into 10 millisecond radio frame, each with 20 slots of 0.5 millisecond duration. It's flexible, support a wide range of data transfer rate, and included FDD and TDD subframes. A special subframe guard interval and reference signal. This feature optimized spectrum use, enable synchronization and channel estimation, and mitigate interference effects. It's a critical component of LTE radio interface for efficient data transfer over the air. Here is LTE protocol stack. The physical layer is responsible for transmission and reception of data over the air interface. It includes various sublayers such as the physical layer control, also known as PLC sublayer, which handle the control and synchronization signals, and the physical layer processing, also known as PLC sublayer, which handle the data modulation and demodulation. The medium access control layer is responsible for controlling the access to the physical layer and ensuring the efficiency use of radio resources. It includes the medium access control, also known as MAC sublayer, which handle to scheduling and prioritization of data transmission, and the radio resource control, also known as ORC sublayer, which handle the signaling and control of the radio resources. The radio link control layer is responsible for segmentation and assembly of data packet and the error control mechanism to ensure reliable data transfer. It includes the radio link control, which handle the segmentation and assembly of data packet, and the packet data coverage protocol, also known as PDCP sublayer, which handle the encryption and compression of data packet. Whereas in LTE, In LTE, bearers refer to a logical channel that are used to transmit data between the UE, also known as user equipment. It's the core network. A bearer is associated with a QoS, quality of service class, which define the characteristic of the data being transmitted, such as its priority, delay tolerance, and packet loss rate. Layer 1, physical layer. LTE device and network communicate using the LTE protocol stack. The physical data connection and network layer comprise it. Layer 2, we have 3 max. The max layer transport user data and control message between the UE and the E node B across the radio interface. Radio link control. The RLC layer ensure reliable radio interface data transmission between the user equipment and the E node B. Packet data coverage gen protocol layer protects user data and control communication between user equipment and Evolve node B through the radio interface by encrypting and compressing header. Layer 3, radio resource control. It's control the creation, maintain and release of radio bearers between user equipment and Evolve node B in the LTE network. Non-access stratum provides support for signaling messages that are exchanged between the user equipment and the core network. Signaling protocols are used to exchange control information between different network elements such as user equipment and Evolve node B and core network node. LTE structure channel. LTE is a mobile communication protocol that makes use of OFDMA, orthogonal frequency division multiple access, to effectively utilize the spectrum and deliver faster data speed. Physical channel and logical channel are the two different kinds of channel that make up the LTE channel structure. Physical channel. Physical downlink shared channel, also known as PDSCH. It used to transmit downlink data from the base station to the user equipment. It is used to transmit user data control information and packaging information. Physical uplink share channel, also known as PUSCH. It is used to transmit uplink data from the user equipment to the base station. Physical broadcast channel, also known as PBCH. It is used to transmit system information to the user equipment. PBCH is transmitted in the first subframe of every radio frame. Physical control format indicator channel, also known as PCFICH. Its carrier information about the number of OFDM symbols used for control information in the downlink. Physical hybrid ARQ indicator channel, which is also known as PHICH. Its carrier the acknowledgement or negative acknowledgement of the downlink hybrid A or Q. Physical downlink control channel PDCH. It carrier downlink control information such as resource allocation, modulation scheme, and HARQ information. Physical uplink control channel, which is also known as PUCCH. It carries uplink control information such as ACK or NACK, scheduling requests, and CQI, which is channel quality indicator feedback. Transportation channel, dedicated traffic channel, DTCH. This channel is used to carry user data between the user equipment and the Evolve Node B. Dedicated control channel. This channel is used to carry control plane messages between the user equipment and the Evolve Node B. Common control channel. This channel is used to carry broadcast messages and packaging message from the eNode B to the user equipment. Multicast channel. This channel is used to deliver multicast and broadcast data to multiple user equipments at the same time. Packaging channel. This channel is used to alert the user equipment of incoming call or messages when it is in idle mode. Broadcast control channel. This channel is used to broadcast system information to the user equipment. Random access channel. This channel is used by the user equipment to initiate a connection with the eNode B. Forward access channel. This channel is used to carry small amount of data such as a signaling messages between the user equipment and the network. Here is a channel estimation. There are two types of reference signal used in LTE for channel estimation. Cell specific reference signal and the user equipment specific reference signal. The CRS is transmitted by the eNode B and is used by all user equipment in the cell for channel estimation. The URS, on the other hand, is specific to each user equipment and it is transmitted by the user equipment itself. It is used for channel estimation in uplink transmission. So I will pass this task to my friends next.
So let's move to next point that it talk about the multiple input and multiple output antenna techniques. Before we observe the utilization of many antennas of reception, this method used two antennas at the receiver end, and the signals received. And this mechanism, known as diversity processing, works to prevent fading. And the MIO, or we can call it, it stands for multiple input and multiple output. Antenna technologies is employed when more than one antenna is used for transmission and more than one antenna is used for reception. Here, the transmitters use many inputs and the receiver use several outputs. So the IMO is a wireless technology that use multiple transmitters and receivers to transfer more data at the same time. And the next point is talk about beam forming. Another important technique is a beamforming, where the linear array allows antennas to transmit in a focused direction. The main advantage of this and this is to reduce interference and increase the capacity for particular UE, or we can call it user equipment, in whose direction the antennas are focused. This technique has become important of 5G technology. Beamforming is a technique associated with antenna arrays. Phase array antennas and adaptive array antennas and resultant signals are then added and transmitted in a particular direction to achieve beamforming. And the next point is network element on LTE radio network. In the Universal Mobile Telecommunication System, or we can call it UMTS, and 3GPP, long-term evolution, or LTE, user equipment, UE, is any device used directly by one end user to communicate. And the UE, or we can call it user equipment. The fundamental functions of the UE include mobility manage, call control, session management, and identity management. One has to understand a fundamental chief. The term mobile station is also known as UE. However, the term UE is in LTE is used not only for a mobile station but also for other user device to communicating with the base station. There are a few main components for the UE of the UE. USIM mobile termination, or we can call it T terminal adapter, and the last one is terminal equipment. So the base station, or we can call it E node B, and GSM base station were connected to the BSC through E1S. And you know what is GSM? GSM is the global system for mobile communication. It's a digital mobile network that is widely used by mobile phone users in Europe and other parts of the world. And the main aim of LTE technologies is to be everywhere, to decrease the cost of controlling radio networks centrally through BSC or ORNC in GSM and UMST technologies. 3GPP introduced SAE, or we can call it system level architecture, which removed the need for BSC or ORNC. So the radio network in LTE consists only of UE, or user equipment, and base station. And there are two important units. The first one is the radio processing units and the demultiplexing unit. The signals from the UE goes to the radio processing unit, which then interacts with the multiplexing unit. The signals then go through the BB, or we can call it baseband units, toward the core network through the CU. The radio processing unit performs functions such as amplification and analog to digital conversion. And the full name of the UMTS is the Universal Mobile Telecommunication System. It's defined as a third generation, or we can call it a 3G mobile network, built on the global GSM standard and compatible with data transfer up to 2 megabits per second. And the next point is the key phenomena in LTE. The first one is talk about the inter-cell interference. By using X2 layer, E node Bs can talk to each other and schedule the resources in order to control interference. The technique is known as ICIC, or we can call it the inter-cell interference coordination. By using this technique, the base stations are able to talk to each other by using X2 interface about this status of the neighbor. Based on this information, radio resources are allocated to the respective UE. So the inter-cell interference, or ICI, is reduced and finished. The X2 message includes information such as HII, or we can call it high interference indicator, or NTP, relative narrowband transmit power, and the last one is OI, or we can call it overload indicator. Based on this, there are 4 frequency planning schemes. The first one is conventional frequency planning, fractional, soft frequency reuse, and the last one is soft fractional frequency reuse. The scheduling. Here we have the scheduling request, or SOR mechanism. The trigger for SOR is the buffer status report, or we can call it BSR. This report contains more information than the SOR. The SOR sends single bit information on data that needs to transmit it through the UE, while the BSR contains details. The UL and DL scheduling are separated and independent and able to take advantage of the different channel conditions using techniques such as round robin and CIMAX, and the last one is proportion fairness. The scheduler works in the ORLC and MAX layers. The quality of service. The quality of service, or we can call it QoS, is essential factors in LTE networks, as it ensures that the network resources are allocated efficiently and that users receive the required level of service. It is achieved through traffic differentiation, admission control, and traffic shaping. These phenomena are constantly being optimized and improved to provide better network performance and to the user experience. The next point is the radio network planning process and the pre-planning phase. The most important element of the pre-planning phase is dimensioning. Based on this, link budget calculations are done, resulting in primary site count and locations. The basic elements include such as link link, bud- link, link calculations, and coverage analysis. And the next point is traffic and capacity analysis. So let's move to the next point is link budget calculations and coverage analysis. The link budget calculation is done to calculate the maximum path loss. So path loss calculations are then used along with the propagation models to find the actual areas that would be covered after the LTE network launch. Some of the key inputs as seen previously for the link budgets include transmitter and receiver power, antenna gains, both transmitter and receiver, couple and the connector losses, the impacts of cell loading, interference gains, and the propagation models. So, how the crucial link budget calculation and coverage analysis are in the pre-planning stage. So, with the consideration for variables, concluding transmission, power, antenna gain, road loss, receiver sensitivity, and noise rigor. Link budget calculation are to use to access the radio connection performed between the base station and the mobile device, and to make sure that the radio networks is designed to fulfill the user's needs for coverage, capacity, and the quality of service. So the next point is the traffic and capacity analysis. The most crucial material in this chapter is the link budget calculation between UMTS and LTE. So the UMTS link budget is established based on subscriber count, traffic modeling, and the site capacity. The LTE link budget is calculated by dividing the total coverage area by the territory covered by a single cell site. Voice real-time data, including video calls, and non-real-time data are the three types of traffic data. Cell rank, channel bandwidth, cell load, IMO, interference, modulation, coding, and the scheduling are among the elements that affect LTE cell throughput. Other factors to consider include traffic analysis, peak data rates, and the average data rate throughout the day and at the busy periods. The overbooking factor, or OBF, is used in capacity planning for urban or suburban and the rural regions. It is the average number of the subscribers who can share a specific channel unit. The total number of the cell site necessary to achieve the capacity needs depends on the relationship between the site capacity and overall data rate. And the next point is the detailed network planning. So, what is configuration planning? Configuration planning is a planning that requires for the base station configuration in order to achieve the necessary coverage and capacity. Input from dimensioning, site survey findings for geographic input for propagation modeling among the addition inputs. The coverage and capacity capacity calculations are performed once more using the different setups for coverage and oriented planning and capacity oriented planning. And the coverage and capacity planning is a planning planning for coverage and capacity entails designing the radio network's capacity and coverage in a great detail. Base station placement and configuration, frequency, band allocation, and network parameter optimization, including handover, thresholds, and radio resource management parameter are all included in this. And planning for coverage and capacity adapts to ensure that the network completely covers the intended area while increasing network capacity, reducing interference. And parameter planning. Parameter planning, it contains such as SI and or signals to interference and noise radio. It defines as a ratio of the average signal power received to the summation of the average interference power and noise power. P or B or physical resource block. The UE or user equipment is connected to the most suitable cell. This suitability is determined after UE monitors the system information and packing of the cell, so it is connected to each other. And the ORS or P interference signal receives power for elements like cell selection and reselection and handover operations. This must be measured against the usable portion of the OFDMA signal due to the fact of that LTE-UES must have at least two receive antennas, and the UE can access to ORS or P and select the receive antenna with the stronger signal. And the ORS or Q interference signal receive quality. This is the ratio of the SOR SP and the total received signal and noise power. It is calculated as a product of the number of P or BS and the ratio of ORS or P and ORSSI. So ORSSI receive signal threat indicator. It is the measurement of the received radio signal power. PCI or physical cell identity. It's used for two main purposes. So the first one is enable cell handover measurement and as a resource allocated parameter. So the enable cell handover measurement reports are done by the UE, and the two ways to assign PCI is one is based on resource element to resource element interference, and another is resource element to PDSCH or PDCCH interference. And the TA, or we can call it a tracking area. Tracking area parameter planning is similar to a location area and routing area planning. When the UE is in the active stage, it is located is known by the network at cell level. However, when it in idle state, and its location is known as the TA level. The next one is simulations. The Second World War saw the development of the Monte Carlo simulation, which is now utilized in a variety of fields by randomly placing the user in a predetermined deployment environment. It is possible to find aggregate interference in LTE to compute the interference and forecast the network capacity. It uses algorithm linked to scheduling and admission control and power control. However, this does not use movement and fading on a tiny scale. The LTE frequency planning. So the the LTE frequency planning, it contains such as spectrum management. In TDD mode, frequencies allocated are unpaired as both the uplink and downlink to share the frequency band. The channel bandwidth assigned to the network is operator dependent. The lower the frequency, the lower the coverage. And spectrum reframing. The spectrum that has been used for GSM or UMTS may be reformed or reused for LTE. The LTE spectrum has been sold at staggering price across the world. Frequency reforming is a great way to enhance the spectrum bands for the operator to roll out LTE. The next point is channel spacing. Channel spacing refers to the separation between adjacent channels in a frequency band. In LTE frequency planning, the channel spacing is typically determined by the available spectrum and the required bandwidth for each channel. And as you can see, here is the formula of the channel spacing. Where BW is the bandwidth, and the conventional frequency planning. Each of sets of subchannels is allocated to a different UE. The allocation is based on bandwidth requirements. As we have seen before, frequency planning can be conventional, fractional, partial, and software frequency reuse. This offers the worst interference, especially at cell edge, as the frequency spectrum is used in all cells without any restrictions. A way to reduce this interference is to reuse the frequency 3 times. And the last one is fractional frequency reuse, or FFR. it used to partition a cell into two parts, with the center area using all frequencies and the edge of area using only 1/3 of the available frequency subchannels. It can be of two types: partial frequency reuse or PFFR and soft frequency reuse SFFR. So in PFFR, all sectors use a common frequency band at equal power, while the SFFR, each sector transmits to the whole frequency band. And the next point, my friends will explain you.
For the next point is LTE radio network optimization. The LTE pre-line optimization refers to the process of testing and optimizing a new LTE network before it is launched commercially. LTE pre-line optimization can be divided into three different turning steps. So for the first turning state is initial turning state. This state involves a CFT, single cell function test, and dry test to check LTE parameter for every cell of an LTE site. The goal is to ensure each cell function correctly and meet coverage and capacity requirements. During the initial turning state, any issue identified during the SCFT or dry test are addressed to optimize each cell before proceeding to the next step of optimization. This step is critical in ensuring that the LTE network functions correctly and meet basic requirements. So cluster turning is the next turning step in LTE pre-line optimization after the initialized turning step. In this step, all cells are tested to ensure that they meet the desired level of quality of service. Once this is confirmed, site or E node B are grouped into clusters. The goal of cluster-based turning is to achieve an optimal level of LTE performed within this cluster. This involves planning dry route among all sites in a particular cluster and among clusters to check the status of LTE parameters such as error rate, throughput, and inter-site handover. The aim is to resolve any boundary issue and ensure that there are no gaps in coverage or perform issues at the boundary between cells. Cluster turning also involves checking all important roads including arterial, VVIP, throughway, and highway. This ensures that the network performs well in high traffic areas and that the user experience is not compromised. The cluster turning step is crucial in achieving an optimal level of network performance and improving the user experience. It helps to ensure that the LTE network is capable of providing the desired level of QoS quality of service and meet the requirements of different scenarios and environments. So the last turning stack, which is network turning stack. The focus of network turning stack in LTE pre-line optimization is to optimize the performance of the entire network or market area. This is achieved through dry tests on agreed route to collect network level parameters and check the different types of LTE and handover. This includes inter-cell or intra-E node B, inter-E node B, VX2 S1, and intra or inter-MNE handover. Border issues are also analyzed and resolved, such as mitigating any interference from external network that may be observed by border side. During the network turning stage, the level of KPI threshold are somewhat related on moving from SCFT to cluster and then on to network level turning. Therefore, they need to be checked and calculated based on the network level LTE parameter collected during such network dry test to achieve the required quality of service of the LTE network. The network turning state ensures that the LTE network meets the desired level of performance and quality. This step is crucial as it helps to ensure that the LTE network is capable of providing and required level of quality of service in different scenarios and environments. For the next point is self-organization network or SON. In LTE, Self-organizing networks are intelligent systems that can automate network management tasks. They can automatically configure network parameters based on performance measurement, optimizing resource usage. The goal of self-organizing network to improve the user experience by providing seamless connectivity and high-quality service while also reducing operational costs for the network operator. In a self-organizing network environment, the network is able to adapt to changing conditions and traffic patterns, making it more efficient and reliable. Self-organizing network is designed to operate in real time, continuously monitoring and the network performance and adjusting network parameters accordingly. This helps to optimize resource usage, reduce interference, and improve the overall performance of the network. The main benefit of SON is that it reduces the need for manual intervention, which can be time-consuming and costly. With SON, the network can self-configuration, self-optimization, and self-healing to improve the overall efficiency and reliability to the network. So self-configuration in LTE is a plug-and-play process that minimizes human intervention and speed up deployment. The eNode B establishes connection with DHCP, DNS server and configuration server, and assign physical cell ID, download cell, manage inventory, and establish neighbor relation. The goal is to automate the deployment process and reduce human error. Here is the graph of the traffic value. For the next one is self-optimization. It's a set of automatic feature in cellular network that optimize network performance, quality of service, and quality of experience by adjusting parameter and configuration in real time without human intervention. SON can improve network performance, reduce operational costs, and minimize customer complaints. Self-optimization automates the process of optimizing network parameter and configuration. It includes convert optimization, capacity optimization, mobility optimization, interference management, and load balancing. The function improve network performance, quality of service, and quality of experience, and minimize the utilization of network resources. Self-healing in telecommunication network refers to the ability of the network automatically detect and recover from fault and failure without human intervention. The network continuously monitors its performance and takes corrective action and resolve issues such as rerouting traffic or isolating faulty components. Redundant equipment and automatic error correction algorithms are used to prevent service disruption. AI and machine learning algorithms can be used to analyze performance data and predict potential problems before they occur, further improving the network reliability and reducing downtime. Overall, self-healing is an essential aspect of network automation that improves the quality of service and reduce the need for human intervention in network maintenance and troubleshooting. For the next point is self-organized network architecture or SON architecture. SON architecture enables network elements to self-configure, optimize their setting and detect and fix issues automatically, reducing the need for manual configuration and optimization. It utilizes various techniques such as dynamic power control, automatic neighbor relation, self-configuration, self-healing, and network failure prediction and prevention. Dynamic power control allows the network to optimize power usage, reducing interference and improving network performance. Automatic neighbor relation help in discovering and maintaining neighbor relation for efficient handover between base stations. Self-configuration enables devices to automatically configure themselves upon deployment, making it easy to add new devices to the network. There are three types of self-organizing network, namely distributed, centralized, and hybrid. So the first one is distribute. Distribute architecture is characterized by having self-optimization function distribute across multiple nodes in the network. This allows for greater scalability and flexibility, as the network can adapt to changing conditions in real time. In a distributed SAN architecture, each node has the ability to self-configure, self-optimize, and self-heal, enabling the network to operate at optimal performance level with minimal human intervention. The downside to this approach is that it requires more sophisticated hardware and software, which can be expensive to deploy and maintain. The second one is centralized SAN architecture. Centralized is the self-optimization function in a single network element. This allows for greater control and visibility for network performance, making it easier to monitor and optimize. Centralized SAN architecture can be especially useful in large and complex networks as it simplifies network management and reduces the need for specialized hardware and software. However, it can also introduce a single point of failure if the centralized element experience a malfunction. And the last one is hybrid SAN architecture. It combines elements of both distributed and centralized. SON, it involves having self-optimization function distributed across multiple nodes in the network, while also having a centralized element that oversees and coordinates the optimization effort. Hybrid SON offers the benefit of both approaches, including greater scalability, flexibility, and control. However, it also requires a high level of coordination between the distributed and centralized elements, which can be challenging to implement. For the key performance indicator, LTE performance parameters are divided into 5 classes. Accessibility is user access to the required service. Returnability, capability of network to return user for providing desired service for time request. Mobility related to handover network ability to provide service to moving user. Availability, percentage of time cell is available to give service to user. Integrity, service quality for the user. Performance indicators are used to optimize the network, allowing the engineer to evaluate how the network is performing with respect to design. Radio network optimization is a continuous activity through the life cycle of any network to meet the threshold of KPI. Capacity crunch can lead to blocking of a new subscriber to service offered by the network operator, but activating the best suitable feature available with the equipment vendor can reduce expense. For the next point is LTE Advanced. LTE Advanced, or known as LTE-A, is an improved version of LTE, also known as 4G+. It incorporates technologies such as carrier aggregation, support for relay node, and multi-antenna technique. LTE-A offers faster speed than LTE, with peak data rate of up to 1 Gbps at a bandwidth of 100 MHz. Release 12 and 11 features improve upon this technology. It has 4 key elements. Here, one carrier aggregation, known as CA, is one of the key features of LTE-A that allow multiple carriers to be combined to increase the bandwidth and data rate. With CA, carriers of different frequency bands can be aggregated to provide faster data rate to user. 2. MIMO, multiple input, multiple output. It is the same from LTE, but in LTE-A perspective, it has 8 antennas in DL and 4 antennas in UL are supported. 3. Coordinate multiple point transmission and reception is a feature that allows multiple cells to work together to serve a single user, which can improve the overall user experience, especially in areas with high traffic or congestion. 4. Relay node is essentially low-power base station that can be used to extend the coverage and capacity of network in areas with poor coverage or high traffic. They can be deployed in a variety of scenarios, such as indoor coverage, rural coverage, and hotspot areas. Thank you for attending this presentation. If you have any question or comment, please feel free to share them with me.